So our ninth learning unit here is on electrochemistry. We're going to split this learning unit into three main skills. The first is learning how to write and balance redox equations and reactions. The second is learning how to diagram and use voltaic cells. And then the third is how to calculate the standard potential for one of those voltaic cells. And then think about how that relates to free energy and equilibrium. So kind of bringing lots of things together here with this last learning unit. So as I hope you've seen here, we've revisited Unit 4 in a lot of ways here. Unit 4 from Gen Chem 1. So Unit 4 from Gen Chem 1 was really all about kind of the main reactions that we do in chemistry. So we did acid-base chemistry, and yeah, we had two entire learning units on acid-base chemistry and buffers and titrations here in Gen Chem 2. And then we talked about sparingly soluble salts and precipitation reactions. We saw that in our complex ionic equilibrium learning unit, where we learned about KSP. And now we're going to expand on the little bit of redox chemistry that we learned last year in Gen Chem 1, and we're going to expand on that. Some things are going to be built on, and some things are going to be completely new. So let's do a little bit of review here from concepts that we learned in Unit 4. And that's just conceptually thinking about what it means to be a redox reaction or an oxidation reduction reaction. In redox reactions, we've got the net movement of electrons from one reactant who has a lesser attraction for those electrons, so they're willing to give them up, to another who is willing to gain them or take them on. And so maybe if you've taken a chemistry course before, you've sort of learned one of these mnemonic devices to help you understand what's going on. So Leo Gur, you can remember Leo the lion says Gur, so losing electrons is oxidation. So something that loses electrons is oxidized. If it gains electrons, it's reduced. And every year I need to fix this. Oxidation is loss. So we don't have the E here, that's part of this. So oxidation is loss, so oil rig. Oxidation is loss, reduction is gain. So it's the I that's part of this. So oxidation is loss, reduction is gain. You can clearly tell I was not an oil rig person. I learned Leo Gur. But however you want to remember it, you have to have up in your brain that if I'm losing something, or losing electrons, that species is oxidized. If I'm gaining electrons, that species is reduced. That's a really important concept to understand. Some other terminology that we'll utilize here. Something that loses electrons is oxidized. We'll also define it as being the reducing agent. Because it's giving up its electrons, it's forcing someone else to be reduced. So it's an agent of reduction. And when we think about identifying things that have been oxidized or reduced, we can look at the oxidation number. So this is a skill that we learned last year. We're going to build on it a little bit here, but also look at it differently. So we can look at oxidation numbers to tell whether or not a species has been oxidized or reduced. So if we increase the oxidation number, we become more positive. That's because we've lost something negative. We've lost those electrons. The opposite is true if something is reduced and gains electrons. So we'd say that that is the oxidizing agent. If it gains electrons, that's because it's forcing someone else to lose theirs. And so we're going to see a decrease in oxidation number. And that oxidation number thing can get a little bit confusing because you become more positive as you lose things. But remember, those things that we're losing are negative, and that's the reason why. So this is actually a new slide from this learning unit to talk about some of the same concepts. So it's the same information that's here, but just kind of put in a new way. Identifying oxidation reduction reactions, again, trading electrons. So I don't think there's necessarily any new information that we have here, but this is nice to kind of highlight. Here's where we see these oxidation numbers that are up there. Remember, anything that exists in its elemental form has an oxidation number of 0. Ions have oxidation numbers that are the charge that we have on those. And so here's, again, another review from Learning Unit 4 that we had last semester, just kind of highlighting the differences that we see here with oxidation numbers and how we assign oxidation numbers. So in Unit 4 from last year, we balanced redox equations using oxidation numbers. So that's how we were able to kind of connect things together. So this is a good review. If this is not familiar and kind of up in your brain, make sure that you kind of review how to assign oxidation numbers. Remember that our final exam for this course is cumulative. So it's Gen Chem 1 and Gen Chem 2. So a lot of the things that we learned last semester are going to be things that you will see on your final exam. All right, so that was just kind of a review of how we assign oxidation numbers. we are going to use a different method for balancing equations in this learning unit. We're going to do what's called the half reaction method. So this method does not require assigning oxidation numbers, but it's important to think about and know how to assign oxidation numbers still. But this is going to be also something that will be easy to apply as we think about whether a solution is acidic or basic. So there's some steps that are going to be part of this process, just like I try to teach you guys with anything else that we learn. If we have a systematic step-by-step way of doing these, it's going to help make it easy for you to continue to do new problems. So I'm not going to go through the details of these right now because I have an example problem that rewrites these steps. So highlighting, we're going to write some half reactions. We're going to have some detailed steps to balance that half reaction. And this is usually where things get a little bit tricky. There's the most steps kind of in this second part where we're balancing these half reactions. Okay, we might need to be scaling our half reactions because if we're trading electrons, we have to make sure that we've got the same number of electrons that we're talking about giving up and then taking on. And then we need to make sure we add these together, include states of matter, all of those pieces of information. So those are the 4 basic steps for balancing a redox reaction in acidic solution. You may see, and this is one extra optional step 5, if you have to balance an equation in basic solution, then you have to do one more step, but this is only if it indicates that you have to do this in basic solution. So we've got one problem here that I'm going to run through. You probably, if you want to take time to write down everything that I have, I would encourage you to pause the video so that you can write it down and then listen to the explanation. And then I will have an extra credit video up online for a problem that you can work through. And we're certainly going to work through solving problems in class. So again, this is our skeleton equation. You notice that we've got a polyatomic anion here. It was probably maybe from sodium or potassium chromate. And then again, we've got iodide here. Again, maybe from potassium or sodium iodide. But those potassium and sodium ions are spectator ions. So we don't have them here in what we refer to as our skeleton equation. So the first step, remember, is to take that skeleton equation and break it apart into 2 half reactions. So again, look for things that are related by the elements that are not oxygen and hydrogen to sort of split things apart. So hopefully we see that there's a chromium here and here. So these 2 belong together as a half reaction. Iodine and iodide. So iodide and iodine here. Those are going to belong together as half reactions. So again, the first thing that we do is just identify redox pairs that we're going to have here, and we set them up to be related in 2 redox half reactions. Okay? Next step, again, this is likely the most involved, so we're going to go through this a little bit more slowly to make sure that we can see how we balance everything here. So when we're looking at this second step, balancing atoms and charges in our half reaction, remember the first thing is we're going to try to balance atoms other than oxygen and hydrogen, since they're likely to be present only in one species. So let's take this guy on the right here. It's a little bit simpler because all we really have is the atom iodine here. So again, we've got I2 over here, an elemental iodine, and we've got only one iodide over here. We need to add a 2 in order to balance this. So this one was pretty straightforward in terms of balancing the atoms. Let's take our chromium here. So again, we've got dichromate and then a chromium 3+ cation here. So let's go ahead and balance the chromiums first. We know we're going to need to add a 2 there to make sure that we've balanced those chromiums. Now we have to balance oxygens and hydrogens. So start first by balancing oxygen atoms by adding water. If I've got 7 oxygens that are over here, I'm going to add 7 waters over here. So balance first with water to balance your oxygens, and then balance any hydrogens with H+. Well, by adding 7 waters over here, I added 14 hydrogen atoms. So I need to add 14 H+ over to this side. Okay, so to recap what we did here, and again, this is the most involved and kind of time-consuming step. Balance atoms first that are non-oxygen and hydrogen atoms. Then go ahead, balance oxygen first by adding water, and then balance hydrogen by adding H+. The next step that we need to do is make sure to balance charge. This is a common place where students can make mistakes because if your coefficients aren't right, your charges aren't going to be right. So let's start on the right side here. On the right side, anything that's in its elemental form is not going to have any charge. So the net charge of everything on the right side here is going to be 0. We've got 2 monoatomic anions, so 2 things that have a -1 charge. So the net charge of everything on our left side is -2. If we want to balance this, I've got -2 on the left, I've got 0 on the right. I need to add 2 negative things on my right to get those charges to balance. So that means this is going to be my oxidation reaction because I'm putting electrons on the right side of the equation. Once I rewrite my oxidation half reaction here, it's going to be 2I- goes to I2 plus 2 electrons. That one was pretty straightforward, not a lot to it. Let's go over to this guy on the left here where we have a lot more to consider. All right, looking at my right side, water contributes no charge, and I've got 2 metal cations that have a +3 charge. So the net of charge on the right side is +6. If we look over on the left here, I've got 1 thing that's -2 charge, and I've got 14 things that are +1 charge. So the net of +14 and -2 is going to be +12. So the net charge on the left side is +12. If I want to have these charges balanced, that means I need to add 6 negative things, 6 electrons to the left side there. Okay? As I pull all of this together and sum everything up, again, I'm going to see that I'm going to have electrons on the left side, which means this is my reduction reaction. If you're ever going through these steps and you see that you're trying to add electrons to the same sides, either making 2 oxidation or 2 reduction reactions, that's a clue that something's not right. Go back and check either your balancing of atoms, your determination of charge, something's a little bit off. But as we add all of this up here, again, I'm going to have 14H plus 1 dichromate anion plus 6 electrons in my reduction reaction makes 2 chromium 3+, and then 7 waters. Okay, so that was step 2. Again, that's the most involved step probably, but also the most prone to kind of having silly little mistakes that can make your math be off. All right, so the third step then is to think about multiplying one or both half reactions by an integer if necessary so that the number of electrons that are gained in my reduction reaction equals the number that are lost in my oxidation half reaction. So in this case, I have to scale this guy up by 3 so that I've got 6 electrons that are being lost in my oxidation reaction equal to 6 electrons that need to be gained in my reduction half reaction. So not a lot really involved in this step other than kind of checking and making sure that I've got a balance between the number of electrons lost and the number of electrons gained. All right, fourth step really just means we're going to add both of these together, crossing off things that appear on both sides, and then allowing us to put back in specific phases or states of matter. So again, electrons by necessity should cancel here. I'm going to have 6 electrons in my reduction reaction, 6 electrons in my oxidation reaction. Right now, I can see that I've got nothing on either of these sides that are present that I'm going to allow to cancel. For example, if I had some water on the left side of this reaction and then water on the right side of this reaction, I could have the net sum of those be something different than what was present on both sides. So not something we need to think about here. Truly, the only thing that cancels out here is my electrons. So everything that was present on the left side becomes reactants. So I've got my 14H+, my dichromate, my 6 iodides. Everything that was on the right side here, I should actually point to here, on the right side here, comes down on the right side of my equation here. So 2 chromium, 7 waters, and then my 3 iodine. I'm going to bring down my states of matter here, whether it's aqueous, liquid, or solid. And at this point, I have balanced this redox reaction in acidic solution. All right, so the last piece was, and this is only necessary if it's asking, is to balance it in basic solution. So if they asked us to balance in basic solution, we're basically going to be adding the same number of hydroxide ions as there are H plus ions. Okay, so what that means is I'm going to add 14 OH minuses to this side because I want them to cancel out and neutralize the 14 H pluses that I have. Okay, but I don't want to undo all of that beautiful work that I did to balance a chemical equation. So in that case, I need to make sure that I put 14 OH minuses on the right. Okay, so now let's see what happens here. When I have 14 H pluses and 14 OH minuses, does that make sense to everybody that that generates 14 waters? Well, I have to remember that I had 7 waters that were on my right. So 14 on my left, 7 on my right is a net of 7 on my left. Okay, so after all of that and after all the dust settles from that, I'm going to have a net of 7 waters on my left. And then this 14 hydroxides, those stick around. So 14 hydroxides on the right. So one of the things that you'll notice is the only thing that really changes, I don't change the number of atoms, the number that I have here because it's still balanced. But what changed is whether I had protons being around, meaning I was in acidic solution, or I've got OH minus being around, meaning that I'm in basic solution. Remember, this is only a step you'll have to do if you're asked to balance the redox equation in basic solution. If there's not any information about balancing in basic solution, this is the final answer for your redox reaction.